Before I begin, let me mention that this will not be a comprehensive course on teleparallelism or teleparallel gravity. However, I'm going to cover some of the main topics, which include the tetrad fields, the Lagrangian formalism, and we'll look at the field equations and the energy momentum and tensor. Now, teleparallelism, it is also called teleparallel gravity, and it was an attempt by Einstein to base a unified theory of electromagnetism and gravity on the mathematical structure of what is called distant parallelism. Now, in this theory, a space-time is characterized by what is called a curvature-free linear connection in conjunction with a metric tensor field, and these both of them are defined in terms of a dynamical tetrad field, right? Okay, so we know that in Einstein theory of gravity, the gravitational field, which requires christoffel symbols, right? And the gravitational field is defined in terms of the Riemannian curvature tensor, which is R mu nu alpha beta, right? However, that theory is incapable of coupling to fermionic fields. And so this shortcoming of the theory requires an alternative theory of gravity, and that is where teleparallelism comes in. So it is also known as the teleparallel equivalent of general relativity, and it is a geometrical theory of gravity in which the tetrad, or also sometimes called the Verbian field, is the dynamical field. So this is a field and this is the dynamical field, or it is also the dynamical variable, and it is constructed in terms of torsion or the torsion tensor, right? Instead of this Riemannian or instead of this curvature tensor, right? So we'll be focusing on this torsion in this course. And in the framework of teleparallel gravity, the coupling of fermions to gravity is achieved from the what is called the contortion tensor. And I'm saying these terms, of course I'm going to define all of these in upcoming lectures or so. And once you are given, or once you set the tetrads or the tetrad fields, then it is possible to construct from them the metric g mu nu, the christoffel symbols, which is represented with this capital lambda lambda mu nu. Sorry, this is actually gamma, my bad. Okay, and also you can make this thing called the torsion-free Levi-Civita connection, which is this thing omega mu AB of E, right? And of course I'll be defining them onwards. Now note over here that the tetrad theory of gravity is a geometrical framework, and it is more general, and it is in agreement with the Riemannian geometry, which it has to be because I said that it's more general, right? And you will see how that is. Okay, now let's move on to our first topic, which is of the tetrad fields. Now, a set of tetrad fields is defined using four orthonormal linearly independent vector fields in space-time. So we can pick E mu 0, you can have E mu 1, E mu 2, and E mu 3, right? And these are orthonormal, and they're linearly independent of each other in space-time. And these vector fields sets up the local reference frame of an observer that moves along some trajectory c, right? So it's something like you have a global space that is defined like this, and in here you have let me switch my eraser like this. So in here you have an observer, right? And this observer uses his own reference frame, which is defined using these four orthonormal basis vectors, right? And then there is the and then this global space, it is defined using some other four orthonormal basis vectors, right? Where the 0, 1 can be considered as the time, while 1, 2, and 3 are your spatial vector fields, right? Okay, nice. So this trajectory where this observer is moving, it is represented by world line, which is x mu of tau, where this tau is the proper time. So let me write it down over here. It is the proper time of the observer, right? So it is the proper time of observer, right? Okay, so now the like I said already, the components, this one, that E0 mu and E, let's define the spatial ones with this I. So I goes from 1 to 3, right? So 1, 2, and 3. These are this 0, 1 is time-like, and this one is space-like vectors. Okay, now let's move on, and let's see that these vector fields A mu A, right, where this A can go from 0 to 3, they transform as covariant vector fields under the coordinate transformations, and they transform as contravariant vector fields under SO3, 1, where 3 is for space and 1 is for time. And these are your Lorentz transformations, which means that you have E tilde A mu, this is the transformation law, lambda AB EB mu, right? So here again, these lambda are the set of lambda AB are representations of your SO3, 1 group, right? And they satisfy the relation. So lambda has to satisfy this relation AC BD eta BD eta AB is equal to eta CD. So the lambda matrices, they satisfy this relation, where this eta is the metric. Now the metric tensor, which is G mu nu, it is acquired by a relation which is given by E B mu E B nu eta AB is equal to G mu nu, right? So, well, I just need to write it once, so let's get rid of this. So G mu nu, which is the metric tensor, it is acquired by this relation, right? Now why do we need the tetrad fields, right? Well, because the tetrad fields, they allow the projection of vectors and tensors in space-time in the local frame of an observer. So in order to measure the field quantities with magnitude and direction both, an observer must project these quantities on the frame that is carried by an observer, which is in this case is this. So, well, then the projection of a vector, say the vector is V mu of x at some position, let's say where x is that position, so at some position x mu on a particular frame is given by V A of x is equal to E A mu of x times the vector field V mu of x, right? So this gives you the projection of this vector V mu of x at some position x mu, right? So now say that you're given a world line, let's call that world line C. Then this world line C is for of an observer, and it is represented by x mu of tau, where again tau is the proper time of the observer. Then you can get easily the velocity of an observer along this world line C, and it is given by u mu of tau is equal to the proper time derivative of your x mu, so which is dx mu over d tau. Now the observer's velocity is identified with a is equal to 0, right? So this the zeroth component of this E mu a is the observer's velocity, and so if that is the case, then you can write E mu 0 is equal to u mu of tau over c, where c is the speed of light, right? So you must differentiate between this c and this c. This is the curve, right? This one is the curve c, where this is the speed of light c. You can set it equal to 1. Most of the time we physicists, we set these quantities equal to 1 because they don't tell us anything about the physics of the situation, so we just get rid of them for simplification, right? Okay, so now we have defined the velocity. What is next is then you can define the acceleration, which is a mu of your observer, and it is specified by the absolute derivative of your velocity, which is this thing. So and along c, of course, which c is the it is the world line of the observer, and then you have, if you take the absolute derivative of this thing, you get du mu over d tau, right, with respect to time. And if I take this, I know that I can define my velocity from this equation. So I'll taking the absolute derivative like this, you have this where d is the absolute derivative, right, and c is just a constant, so I can throw it out and I'm left with e mu 0 over d tau, right? Okay, so what this gives you is c u alpha and the covariant derivative alpha e mu 0, right? All I have done is use this equation and taken the absolute derivative of the velocity, which is this thing, right? Okay, nice. Now you can write this covariant derivative. You know, we can write it if you're here watching this video, you must know things from your course on general relativity or just a differential geometry, where you learn that the covariant derivative is defined in terms of the christoffel connections, right? And so I can define, or I can write this derivative de mu 0 with respect to time, proper time, as d e mu 0 over d tau plus the christoffel symbol mu alpha beta dx alpha over d tau e beta 0. And then you can expand this again, and you can write it, you can expand and you can write it, well, I'll write it, it's all right, dx alpha over d tau times de mu 0 over d tau plus your christoffel symbols mu alpha beta and dx alpha over d tau e beta 0. And then we know that this thing is nothing but you have this thing as your u alpha, and this part is just the covariant derivative acting on the vector field E0. So you have the covariant derivative E mu 0. And so I just did this to tell you from where I got this thing, right? So this thing is actually this thing, right? And which is in turn this thing which we were doing over here, right? Okay, beautiful. Now so this tells you that this e mu 0 gives you the velocity and the acceleration of an observer that is moving along the world line c. Now, given a set of tetrad fields for which this e mu 0 describes a congruence of time-like curves is adapted to a particular class of observers, specifically to observers that are characterized by the velocity field, which we have defined again using this equation, which will just give you u mu is equal to c e mu 0, right? Okay, now it is provided with the acceleration a mu. Now let's look at a case where you say that your e a mu goes to delta a mu, right? In the limit where r goes to infinity, right? And then you have this thing that e a mu it is adapted to stationary observers at space like infinity, right? Okay, now moving forward, the geometrical attribution of the tetrad field as an observer's frame may be given in the view of the acceleration of the frame along an arbitrary path. So let's call that path x mu of tau of the observer, right? So that's the arbitrary path of the observer. And as I have shown, the acceleration of the whole frame is intent on the absolute derivative of this e mu a, right? So, and it is along this path that is defined with this x mu of tau. Now, thus assuming that the observer carries this orthonormal tetrad frame, which is your this one, right, e a mu, then the acceleration of the frame along the path is prescribed by the absolute derivative of e mu a over d tau, right, is equal to some phi b a e mu b, right? This is the acceleration of the frame along that path c, right? Now here this phi ab, you can write it as phi ab, is identified as anti-symmetric acceleration tensor, right? So it is an anti-symmetric acceleration tensor. Okay, nice. Now well, following from this equation, let me just put it in box. Following from this, you get your phi ba as e b mu d e mu a over d tau times yes, times this thing EB mu, and it is equal to, then we know that we already defined this over here. If you look at it, it was defined as this thing, right? So I just have to write EB mu, and then I have this U lambda, okay, right from here. So I'm just changing indices now. So we have del lambda E mu A, right? And that's how you define the anti-symmetric acceleration tensor. Now the acceleration vector A mu, it can be projected on a frame to give something which is AB is equal to EB mu A mu, and if I expand this, I get C, which is the speed of light, times EB mu U alpha, and the covariant derivative E mu of 0, right? And this thing is then, because we know that phi is defined like this, then I can just have C times phi b of 0, right? Where this thing is your phi b 0. Now this implies, if you look at it, this just implies that this A, B and phi are not separate translational accelerations of the frame. So they are the same, in fact. Now you can rewrite the expression for A mu as, well, let's just divide it by C. So you can rewrite the expression for A mu, the acceleration, as U alpha covariant derivative of E mu 0, which is then further equal to U alpha covariant derivative of E b 0. Wait, I'm just writing the exact same thing again. So let me get rid of this. You can write it as the covariant derivative like this of U mu, right? And which is then equal to dx alpha over ds, where this s is the space-time path, and you have du mu over dx alpha plus the christoffel symbol mu alpha beta u beta, right? Where again this is just the this is your, well, it's your covariant derivative, and then you have this thing is equal to the double derivative d 2x mu over ds squared plus your christoffel connection alpha beta dx alpha over ds dx beta over ds. Wow, okay, so hopefully you did not get lost in the index gymnastics, I would say. But now if you say that your u mu which is equal to c times e mu of 0, if you say that this represents a geodesic trajectory, then the frame is in a free fall. And if a frame is in a free fall, then you can also write A mu over C as being equal to phi 0 I, which is equal to 0. Now with this, then you can conclude that the non-vanishing values of the latter quantities represents the initial acceleration of the frame. And since since you know that the tetrads are orthonormal vectors, then what you can do is you can rewrite this equation for phi, right, which is this one. You can rewrite it as phi ba is equal to you can rewrite it as u lambda e mu a times the covariant derivative of this field e b mu, right? And in here now, note that again, I just mention it, that this quantity, which is this thing, it is just the covariant derivative of the field, which is represented as partial lambda e b mu minus this christoffel symbol sigma lambda mu times e b sigma. Right, now what you can do is, from here I'm just going to use an identity which is given as partial lambda e b mu minus the christoffel symbol lambda mu e b sigma, and if I add to this if I add to this the metric compatible torsion, which is defined as this omega b lambda c times e c mu, and this is then equal to 0. So this is an identity, and here this omega b lambda c is the metric compatible torsion free Levi-Civita connection, and it is defined as omega mu a b is equal to minus 1 by 2 e c mu times I'm going to write it down right now, and I'll define it in the next step. So it is times this capital omega a b c minus omega b a c minus omega c a b, right? And now remember that we are still in our we said that our dynamical fields are the tetrad fields. So this omega a b c, then you should know that it is in terms of those tetrad fields, and so I will write it down that it is simply equal to e a nu times e mu b partial mu e nu c minus e mu c partial mu e nu b, right? Okay, and now using this, then I can express this field, this tensor phi ba, as being equal to c times e mu 0 times this omega b mu a, right? Okay, good. Now here I am going to define a tensor which is known as actually the contortion tensor, which is k a mu b. So this tensor is called the contortion tensor, and I'm going to define it using this omega omega a mu b, and such that this thing is equal to minus k a mu b. So now all I have to do to define this tensor is just add a negative sign to this omega, and I'm going to write it in terms of the torsion tensor, and which is actually torsion tensor is your t lambda mu nu. So this is your torsion tensor, and writing the contortion tensor in terms of this torsion tensor, I'll have mu a b, k mu a b is equal to 1 by 2 e lambda a e nu b times the torsion tensors mu nu lambda mu nu plus t nu lambda mu plus t mu lambda nu. Right, now this torsion tensor is such that your T lambda mu nu is equal to E a lambda T a mu nu. Right? Okay. So again, now this thing is called the contortion tensor, and so we finally arrive at a result which is for the phi AB, which would be equal to, now in terms of the torsion tensor, it is written as C over 2 times T0 AB, right? Because we're writing it for the 0th part, so you have plus T A0B plus T B0A, and that's it. So this is your symmetric anti-symmetric tensor, right? Your anti-symmetric acceleration tensor, and it is written in terms of the torsion tensor, right? Okay, so you have to see over here that if you look at this expression, you'll immediately see that it is not invariant under the SO3, 1 group. So it is, this thing is under this thing, it is not invariant, right? However, it is indeed invariant under the coordinate transformations. So let me write it like this: coordinate transformations. This thing, it is invariant under coordinate transformations. Okay, so and also that the values of this this field phi AB for a specific tetrad field can be used to characterize the frame, right? And so we can interpret this phi AB as the inertial acceleration along the trajectory that is x mu of tau, right? So let's conclude this video or lecture over here by let me just summarize everything. So in a nutshell, we have that for any given set of tetrad fields for some random space-time, its geometrical interpretation can be given by well, first of all, you conveniently identify the velocity u mu is equal to c e mu 0. So we derived this result of the field that is along with the orientation of the components, which are e mu 1, e mu 2, and e mu 3, right? And the second point is that the values of the anti-symmetric acceleration tensor, which is this phi AB, right? And the values for this characterizes the inertial state of frame. So this is going to characterize the inertial state of your frame. So these are the two main things that you should have gotten out of this lecture. And next time I'm going to look at the Lagrangian formalism for this teleparallel gravity.